These two pendulums start 1 millimeter apart, and seconds later they disagree about where reality is. Watch the blue tip. Both pendulums fall together, swing left together, and for a moment they look like copies. Then one flips over the top, the other kicks sideways. A few seconds after that, they're tracing completely different paths. No motor changes speed, nobody bumps the table. The only difference is that tiny gap at the start. So here's the irritating part. If I reset both perfectly, each one repeats its own motion perfectly. The machine isn't choosing randomly, its future is already determined. But if my reset is off by 1 millimeter, or one grain of dust changes the speed, that future can become useless for predicting the real pendulum. Deterministic yet practically unpredictable. I got those two ideas tangled up the first time too. They sound like opposites. They're allowed to coexist because the double pendulum takes small errors and stretches them fast. We're going to keep one blue pendulum and one yellow copy on screen, and the gap between them is our main character. Right now that gap is almost invisible. In a few swings it'll own the whole frame. The question is where all that separation comes from, because a normal pendulum certainly doesn't behave like this. A normal pendulum doesn't amplify the gap like that. Give two ordinary pendulums nearly the same push, and they stay nearly together. Their timing may drift, but politely. The second arm ruins the politeness. Keep your eye on the middle joint. When the upper arm moves, it carries that joint through space, so the lower arm's pivot is moving under it. Then the lower arm pulls back on the upper one. Energy can shuttle between them. Upper arm, upper arm again. Sometimes the transfer gives the lower mass enough speed to loop over the joint. Sometimes it misses by a hair. That near miss matters because a full rotation and a backward swing lead into wildly different next moves. Here's a useful picture. A single pendulum needs two numbers to describe its state, its angle, and its angular speed. A double pendulum needs four, two angles, two speeds. So the real state isn't the shape you see in one frame. Two pendulums can have identical looking arms while their joints are moving differently, and a tenth of a second later the disguise falls apart. Honestly, velocity being invisible is one of physics' ruder tricks. We need somewhere to put all four numbers. Once we do that, the apparent mess becomes a smooth path, and then we can watch exactly how nearby futures split. That dot gives us the map we were missing. Every possible combination of angles and speeds is one location in a four-dimensional space. 4 dimensions are terrible television, so I'm going to cheat responsibly. We'll hold two of the numbers quiet and draw a two-dimensional slice. One pendulum becomes one moving dot. As the arms swing, the dot draws a continuous curve through state space. No teleporting, no dice rolls, just the laws of motion, carrying the state to its next location. Now place the yellow copy almost on top of the blue one. At first, their state space paths are indistinguishable. Then the flow stretches their tiny separation in one direction, folds the paths through the available region, and stretches them again. Stretch, fold, repeat. That's the basic machinery of chaos. Think of kneading dough, except the dough is made of possible futures, which is a sentence I regret slightly. The folding matters because the system has limited energy. The trajectories can't simply fly apart forever. They stay inside an allowed region while becoming thoroughly rearranged within it. And here is our screenshot frame. One narrow bundle of almost identical starting states turns into long colored strands, woven across the allowed region. Each strand obeys the same equations. Their neighborhood has been shredded, but saying the gap grows is still vague. How fast does it grow? Because the answer decides whether we can predict 10 swings, 100 swings, or basically lunch. The gap often grows exponentially. That means it gets multiplied by roughly the same factor over equal chunks of time. Suppose our error doubles every second. 1 millimeter becomes 2, then 4, 8, 16. After 10 doublings, it's over a meter. The exact rate changes with the pendulum's energy and where it travels, but the idea has a name, the Lyapunov exponent. Ugly notation incoming, and I'm sorry on behalf of mathematicians. We write the separation as epsilon of t, approximately epsilon 0 times e to the lambda t. Lambda tells us how aggressively nearby states separate. Positive lambda means prediction errors tend to grow exponentially. So buying a ruler 10 times more precise doesn't buy 10 times more prediction time. It adds a fixed amount, because exponential growth chews through extra decimal places one after another. That's the mean little punchline. Better measurements help, absolutely. They never provide infinite foresight. To predict indefinitely, we need the starting angles and speeds with infinitely many exact digits, plus a flawless model, plus no air currents, flexing rods, bearing friction, or nearby cat deciding this is now an experiment about cats. We don't get that package. Still, chaos doesn't mean every moment is equally mysterious. For a short while, the blue and yellow paths remain close. Prediction has a horizon, and we can actually watch that horizon arrive. That horizon explains failed forecasts, but we still owe the title an answer. Why doesn't the motion repeat? For an exact repeat, all four-state numbers must return to their earlier values at the same instant, both angles and both angular speeds. Returning to the same visible shape isn't enough. One joint might be moving forward instead of backward, or moving faster, and the next swing immediately changes. In state space, a truly repeating motion forms a closed loop. The dot comes back to the exact same state, then traces the same loop forever. Double pendulums do have special periodic motions like this. That's the tiny technical caveat hiding under the dramatic title. With carefully chosen starting conditions, repetition is possible. Most starts miss those loops. In the chaotic regime, the trajectory wins through state space and can pass extremely close to an earlier point without landing exactly on it. Close feels convincing on a screen. The growing error notices. That almost return launches a future which may soon look unrelated. So two swings never repeat is everyday language for something more precise. Generic chaotic motion doesn't settle into an exact cycle, and finite measurements can't tell us whether we're sitting on one of the exceptional periodic paths anyway. The rules preserve a strange kind of order, though. The motion has boundaries. Energy still constrains where it can go. The path is unpredictable without being arbitrary, and that gives us one last picture I really like. Instead of asking where one pendulum goes forever, color every starting position by what happens next. Blue means the lower arm's first full flip goes clockwise. Yellow means counterclockwise. Pink means it doesn't flip during our time window. From far away, the map has broad regions. Move the initial angle a little, and the outcome usually stays the same. Now zoom near a boundary. The colors start threading between one another. Zoom again, and thinner threads appear. A tiny change can cross the boundary and switch the outcome. This is the picture chaos was building toward. A weather map for possible futures, with calm neighborhoods and absurdly detailed borders. It also fixes a common misunderstanding. Chaos doesn't erase structure. Look at all that structure. It makes the boundary between outcomes so intricate that finite precision eventually matters. We can predict distributions, energy limits, and short-term motion even when one long trajectory escapes us. Weather forecasting lives with the same basic problem, just with several billion more moving parts and fewer convenient metal rods. So the double pendulum isn't random, and it isn't secretly repeating where we can't see. It follows its equations exactly while nearby futures peel away from each other, then fold back through the same allowed space. And here's the thing that still bugs me. Somewhere inside this ridiculous color map are those perfectly repeating loops, balanced on exact starting conditions like needles. The equations know precisely where every needle is. We usually don't.